Okay, so we begin now with a switch, right, to stochastic identification. Stochastic identification is the name that, let me see how this looks, well, not so great, but you can kind of read it. So, in some instances that arise quite often in civil engineering in particular, we are not able to control the loading that is acting on a structure. That is, we cannot, for one reason, we cannot turn off the ambient excitation, or the owner of the facility or whatever it is does not allow, or the conditions do not permit that one impose known excitations to the system. So you're forced to be working with whatever excitation is driving the system. For example, in a bridge it might be just the traffic loads, in a building it might be just the wind loads, and things of that nature. Now, it is important to note from the very beginning that stochastic identification is also known as output-only identification. Basically, you're doing ID only with the output, not with the input. It must be understood that this does not really mean that the input can be anything. Because if you take the position that the input can be anything, then the output can be anything. That is, if you give me a set of outputs, I can imagine that the system is anything I want, and there is some sort of inputs that will produce that output. Okay? So in the linear system context. So, when we say that we are operating only on the output, we don't really mean that we know nothing about the input. We actually make certain assumptions about what the nature of the input is. We just don't know the input as a deterministic signal, okay, or signals. But we do say, for example, that the input is broadband, and idealized often as white, and so on. So, under certain assumptions, we are able to operate. Now, the system that we assume is generating the data now is like this. Just like before, right? Now, when we had known input, over here we would write BD UK, right? Now, since we don't know what the UK is or where they are applied, instead of putting BD UK that we don't know, we replace the BD UK by omega K. Now, remember, the fact that we don't know it doesn't mean that it doesn't exist. There is some BD UK that is hidden in there. We just don't know what it is. And so we are simply saying it's WK. Okay? Now, the output, YK, is CD XK. And in general, there could be a D, right, times UK. And in addition to the D, maybe there is no D, but there's usually noise in the measurements, and we normally specify it at VK. This could be just purely noise, that is the fact that what we're measuring is not exactly the state times CD, or it could be that it's noise plus the effect of some D that was there. We don't know. But the point is that we assume that equations 1 and 2 are the ones that generate the data that we are observing. Okay? The data that we are observing, the output data, is assumed to come from a system like that. Now, where's the eraser? Here. Okay. So what we will assume is that omega K times omega K transpose, that is this vector times itself, has an expectation which is Q, okay, and that omega K and omega K plus I transpose has an expectation which is 0 for I not equal to 0. In fact, this is the same as that. Except, so when I is equal to 0, of course, something is always correlated with itself, right? And in this case, we say that the expected value of omega k transpose is Q. But the expected value of omega k and omega k plus I for any I that is not equal to 0, we say it's 0. That is the same thing as assuming that omega k is white noise. Okay? We're assuming that omega k is white noise. Now here there is a second to ponder, I guess. When we write these equations, this is for any time step, right? Now, perfect white noise doesn't exist in reality. Because anything, well, it can be shown that in order to have perfect white noise, you have to have infinite energy and so on. I mean, something that is completely correlated with itself for any small time is essentially impossible without infinite energy to do it. So when we say white noise, we really mean white noise within a certain frequency band. Now, just imagine this. You may have an omega k which is from ambient vibration from the wind or something over a certain period that, you know, if the distance between k and k plus 1 is reasonable, then you can expect that this will be okay. But if you make the time step too small, it's no longer logical to assume that omega k and omega k plus 1 is 0, right? Because at a thousandths, at a hundred thousandths of a second, it's not true that what's happening now is not correlated to what's happening in a thousandths of a second after, or even shorter, right? This is normally not discussed, and one normally just states this, but it is important to keep it in mind, because this idealization that this is 0 unless you have the same thing is valid within certain limitations, right? Now getting back to theory, that's it. We assume that omega k transpose is Q. We also assume that this thing, Vk, which also comes from either measurement noise or the sum of measurement noise from a direct transmission, that is, we say that the expected value of Vk transpose is R, right? And once again, and I'll erase it, we assume that the expected value of Vk and Vk plus I transpose is 0 if I is not equal to 0. That is, we also assume that the measurement noise, or the term that we normally traditionally call the measurement noise, is in fact also white noise, or idealizable as white noise. Okay? Now these are basically the two assumptions that we make. And I will put them over here. Q is the expected value of omega k transpose, and R is the expected value of Vk transpose. Okay? Now, one thing, for example, is this, which we will come back later in the discussions. What is the rank of Q? Q is a matrix, omega k has n, right? So X belongs to real n by 1, right? Therefore, it's evident that Q, it's a matrix that is also real and is n by n. So Q is a matrix that is n by n, but it's important to recognize that Q comes from some loading, right? So if you actually looked at what omega k is actually BD times something that we don't know. So that's something that we don't know. We could call it, well, we can leave it as UK if you'd like. And then if we transpose that, that's UK transpose times BD transpose, right? So this is really what Q is. Now, if the excitation UK is acting at 3 degrees of freedom, then BD has 3 columns, and this matrix is only rank 3, right? Even if N was 55. Therefore, the thing to keep in mind is that the rank of Q is, even though Q is an N by N matrix, is not really rank N, right? It's rank, well, the rank of Q is the number of independent excitations, even though we don't know them, that are acting on the structure. In general, even if you assume, for example, that in a building like this, you have a wind load acting on every level, even if you assume that, then in a 4-story structure, the UK would be 4 things, right? And the BD would be a matrix with 4. So the rank of Q here would be 4, right? The rank of Q would be 4, not 8, even though the state here, right, is of dimension 8. Even though this vector has 8 entries in theory here, because we're not saying what it is, the rank of Q is no more than 4, or no more than half the order. All right? Keep that in the back of your mind. All right, so with this in mind, then, we begin the process. What is, well, before that, what is our objective? Our objective, when we knew the input, was to calculate A, B, C, and D. Well, in this particular case, we don't know, there is no such thing as asking the question, what is B? Because that makes no sense to ask what is B. We have no idea. And we cannot ask what is D. We have no idea either. So the objective in the stochastic ID is to get AD and CD, right? No B and no D. Now, given AD and CD, if you go to Jordan canonical form, that means that we can do D to C, right? If we do a D to C, that means that we can get AC and also CC, which is the same as this. That means that we can get the eigenvalues and the eigenvectors of the system, right? Because to get the eigenvalues and the eigenvectors, all you need is A and C. We cannot, however, talk about what is the transfer function or the transfer matrix, because for that we would need B. In other words, we cannot talk about input-output relations because we don't have input locations. So our objective is to calculate AD and CD. So, which of course after that we take a discrete to continuous and so on. So our first step is to take equation 1. I'm going to erase equation 2 to give myself a little space. I'll put it back again later. What we want to do is take equation 1 and we want to multiply it by its transpose. So we want to calculate x at k plus 1 times x at k plus 1 transpose. Okay? Let's see what that is. So that means simply that it's this times the transpose of that. So the transpose of that, I'm going to write it here, is that times its transpose. So its transpose is xk transpose times AD transpose plus omega k transpose, right? So from that, we can get, try the green for a minute, we get AD times xk multiplied times xk transpose times AD transpose plus we get AD times xk times omega k transpose, and we get plus omega k times xk transpose times AD transpose. Unfortunately, this colors, neither one is looking too great. Plus omega k transpose. Okay. Now, that's the product of these two things. So that is equal to xk times xk transpose. Now I'm going to take expectations of this. And that is the expectation of xk and xk transpose. And we're going to call the actually not xk, it was xk plus 1, right? To be really precise. So to be really precise, this is xk plus 1, xk plus 1. So the expectation of xk plus 1 transpose is this. We're going to call that sigma, capital sigma. That is the covariance of the state at k plus 1. Okay? Now, it turns out that the covariance of the state at k plus 1 is the same as the covariance of the state at k, is the covariance of the state at any time, because the way that the system is assumed to be operating is in steady state, right? This is a signal that is just white noise, is not getting bigger or smaller. This is the same thing. This is just operating in steady state. So the state has a covariance which is like this, which is stationary. It's not changing with time. Therefore, that is equal to this. Now, if we take the expectations here, AD is just a constant matrix. And the expectation now applies to xk, xk transpose, and that is also sigma, because as I noted, the expectation does not depend on the k of the state. This term here, I'm sorry, and then AD transpose, right? Now this term, this here is the expectation between the product of the state and WK. Now we can see that the state at k, if you look at this equation, right? The state at k cannot be influenced by WK because they are at the same time. The state at k plus 1 could be influenced by WK, but not the state at k. So this thing here has an expectation which is 0. The same thing happens here, that's just the transpose. And the expectation of omega k transpose, we already gave it a name, and we called it Q, right? So we have developed, at this point, the first equation for a stochastic ID. And that first equation, we will store it over here. It reads sigma is equal to AD times sigma times AD transpose plus Q. Okay? That's the first equation we've just developed, which in words states the covariance of the state under steady state response for a stochastic stochastic loading that is white is equal to the discrete time matrix times itself times the discrete time matrix transpose plus Q. All right? That's it. That's one equation. Now, the next equation that we will do comes from looking at the output equation. Of course, this is all we could do with the state, right? We got that. Now, what we want to do before we look at the output equation, well, not before, we want to develop what is y at k plus I. So let's begin with y at k. Y at k is equal to CD x at k plus vk, right? Now from that, you also see that y at k plus 1 is equal to CD times x at k plus 1 plus v at k plus 1, right? But from here you can see that y at k plus 1 is equal to CD, and then what is x at k plus 1? Is equal to AD x at k plus omega at k, right? Plus v at k plus 1. Correct? Therefore, y at k plus 1 is equal to CD AD x at k plus CD omega at k plus v at k plus 1. Okay? Now, I'll do one more. What is y at k plus 2? Well, it is equal to CD x at k plus 2 plus v at k plus 2, right? But that means that y at k plus 2 is equal to CD. Now x at k plus 2 is AD times x at k plus 1 plus omega at k plus 1, right? That was x at k plus 2 plus v